Hello, welcome. Today we will start hazard identification techniques. Under hazard identification, the first thing to do is prepare a hazard list, which is known as preliminary hazard list. So, the content of today's presentation is hazard identification and analysis techniques, preliminary hazard list. So, how do you get the list? So, for that purpose, there are few things like preliminary hazard list overview, hazard list methodology, PHL worksheets, and this worksheet will be filled up using information related to hazardous energy sources and hazardous processes and events, and after that two cases will be discussed, so that you will understand that how this total concept of identification of preliminary hazard list will be completed. Again, this lecture has been taken from hazard analysis techniques for system safety by Erickson. Okay. So, here few concepts. One is this engineering development life cycle model. Any product or process gone through the life cycle of it. Being industrial safety engineering the subject, so we are more interested in process life cycle, and you just see that when you think of developing a process, first is the concept generation. What purpose it will serve, what is the requirement, who are going to use, that means what the customers, the customer requirements, all those things come under concept definition. For example, if we think the pressure tank system, what we have discussed earlier. So, and you have seen that there is a pressure tank, there is pump, the total the other part. So, now if you think of that what is the requirement of this pressure tank, then it is basically the gas at high pressure will be stored and which will ultimately be distributed to utility equipment. So, that means this is what is to be stored, how much to be stored, what will be the pressure range and all those things, and who are going to be used. This is what is we are talking about the customer requirement here. But if we talk of a big plant like going to open a steel making plant or maybe establishing an engineering project division. So, all those things, these are the big things. There also you please keep in mind that the concept definition means it is the starting point for any engineering system development. Then from the concept definition means knowing the customer's requirements and other thing. So, ultimately what will happen, there can be many ideas. So, some of the ideas will be better ideas, and finally, one of the idea will be selected, and then the detailed design of this product or process will be started by design and development, and here preliminary design, detailed design and testing will be done. Once these things are completed, then come the production and operation including maintenance. Then finally, you will think of at the end of the life cycle the process of the system will be disposed of. So, this is what is the totality. In the PTD concept, I said that design, build, then operation, maintenance, then disposal, the same thing. And you see what we are talking about, that hazard are induced in a system during the design and operation. So, this is a very important part, design part. Here hazard are induced, obviously during operation means in each stage also hazard can be induced, but it is the design life cycle of a system that required to be analyzed for hazard identification. Mean when you are interested to identify the hazard of a system, you have to first understand the total life cycle of the system, and then you must assume that hazard will be induced at each stages of this system life cycle, and you have to identify all those possible hazards at the design stage, even in the before the design, so that though the action or protection against the hazard will be built maximally in the design stage. Okay. So, now when we are talking about hazard identification techniques, we are talking about techniques which are applicable to the system life cycle. Some techniques can be applicable to the entire all the stages of a life cycle, sometimes techniques may be a particular stage, but there are multiple techniques which are developed in the academic and industry arena, and some of the techniques are very popular, and some are extensively used in industries, and some are research type or research oriented, having scope for academic development. So, there are many ways, different hazard identification techniques you will find out, and ultimately you have to use those techniques appropriately in the design stage itself. Okay, so that hazards are identified and hazards are what I can say protected, prevented to recur or occur, so that people will be protected. Okay. So, let us see that what are the different techniques that are available till now. You see, there are lots of techniques. I am naming a few: preliminary hazard list, preliminary hazard analysis, safety requirements criticality analysis, subsystem hazard analysis, system hazard analysis, operations and support hazard analysis, health hazard analysis, fault tree analysis, failure mode and effect analysis, fault hazard analysis, functional hazard analysis, Schnitt circuit analysis, software Schnitt circuit analysis, Petri net, Markov chain, barrier analysis, bend bin analysis, so many, software hazard analysis, and so far I know that there are more than 50 hazard identification techniques already available in the literature. Why such a huge number of techniques? The reason is in the context of its application. So, some techniques are applicable in a particular context, in a particular design stage of the system life cycle, and the commonly used techniques what I have come across so far, I have seen that what if checklist is heavily used, preliminary hazard analysis is used, HAZOP, failure mode and effect analysis, failure mode effect criticality analysis, fault tree analysis, and then event tree analysis. So, these are the few things used mostly, and other techniques like your hierarchical task analysis HTA, which is hierarchical task analysis. Okay. And including human error analysis, is another important one. And from software engineer hazards point of view, Petri net is used, Petri net analysis. Okay. So, the logic behind so many analysis techniques, identification analysis techniques, I told you that you just think of a system, engineering system. You will find out that the system comprises of human, then machine, environment, software. So, human, machine, environment, software. Obviously, there will be interface between them. So, interface between them will be there. Okay. So, now what are the techniques which are applicable to machine related hazard analysis, then environment related hazard analysis, software related hazard analysis, human related hazard analysis. You think of a boiler, there is a process going on. You think of a chemical reactor, some process going on. So, that means that there will be another one is that another category is process. So, what are the technique that will be used for process hazard analysis? Okay. So, second thing is that a system will be composed of several subsystem, system to subsystem, several subsystem, then several subsystem, then finally the components will become. So, a system will be composed of several subsystem and finally a lot of component, all those things. So, you may be, when we are talking about the hazard analysis, obviously the first thing is the system hazard analysis. So, that means now you can go by system breakdown structure, you find out the system components by system, subsystem, subsystem to say component level breakup, and then at the component level find out the hazards, then at the subsystem level find out the hazards and subsystem level hazards, and finally aggregated all will give you the system level hazard. Okay. So, that means at what level of hazard identification and analysis you are doing, that also dictate what kind of technique you will be using. So, that means essentially what I mean to say that it is that the which part of the hazard is considered, which part of a system, and second one is basically that what level of analysis you want, level of analysis you want, and depending on the two, what will happen, you will choose. For example, what if and preliminary hazard analysis, these are very much used for any kind of things like human, machine, environment, process. It is maybe at the total system level or maybe at the component level it is possible. Hazard and operability studies, it is mostly used in process industries, HAZOP. Failure mode and effect analysis, which mostly used for machine and equipment related items. Fault tree analysis, when you want to dig down to from the top level events to the basic events, means suppose system level failure to the component level causes, then like system breakdown structure, there will be the system failure also will be understood through different why analysis with gates and symbols that will give you fault tree. So, fault tree is a little higher level analysis, it can be applicable to everything. Event tree, fault tree, then HTA and human error, that human hazard analysis. Petri net for software hazard analysis. So, when you think of that environment contribution, there is environment related analysis. So, of late what happened that there have been developments by which that some of the techniques which are originally developed for a particular context, they are expanded to other context or other situation. For example, the HAZOP can be used in maintenance also. So, that is known as maintenance operability studies. So, in that sense, that is why there are so many hazard analysis techniques are there. We are not able to tell you all the techniques, but some of the techniques we will be discussed, and today in this particular lecture I will be discussing this preliminary hazard list. So, keep in mind there are multiple of techniques, those are known as hazard identification techniques, sometimes we say hazard analysis techniques also, but whatever may be, hazard identification is the first stage, then followed by hazard analysis, and in any system there will be either process, it can be a chemical type continuous process, can be a discrete type process also. So, there will be set of several equipment or machines, there will be they may be software controlled, may not be software controlled. So, there will be people, that means human intervened system or subsystem or component, or maybe automated or semi automated system, subsystem and components. So, depending on where you want to concentrate, if you are concentrating on human error, it is better you follow a hierarchical task analysis followed by any of the human error analysis techniques. So, we have some lectures on human error analysis in the later stages. Similarly, if you are interested to know most of the equipment type of hazards like your pump, motor, conveyor system, so then perhaps this failure mode and effect analysis will be a better one. If you think no, your system is process oriented like a chemical, like your petrochemical industry, like oil and gas industry, like even in steel making, there are different kind of continuous processes are there, where the process parameters are known and their design intent are known, and they are designed in that manner. So, and through piping and instrumentation diagram PNID, that the total system can be explained. Under such situation, HAZOP is wonderful. Okay. So, these PHA or PHL, PHA, HAZOP, FMEA, all those things basically they can be applied at the system level, also subsystem level. So, but depending on the quantum of the system, if it is a very large system, it will be intractable. So, you have to break the system into subsystem to component level and then apply. By saying this, I am not saying that you do not go for other techniques, you may go for other techniques. There are many techniques gradually are being developed, but this is a guideline. So, my guideline is, when you are dealing with a process where the pressure, temperature, flow, current and all those process parameters are available, their design intent are known, their operation details are easy to are captured. So, I think the process deviation, parameter deviation will be a better measure, go for HAZOP. Suppose you are dealing with a conveyor system or a crane or any discrete machines like in the workshop what we see, then it is better you go for failure mode and effect analysis. Okay. Suppose you have done the PHA, HAZOP, FMA at the maybe system or subsystem level, and you want to further dig you found out the top level accidents that can happen from this analysis, and you want to further dig down to the root cause level, where this faulty analysis will give you wonderful result. Okay. So, this is the basis for why so many techniques are developed, and you find out which of the techniques will be better suited for your system, for your subsystem, for your component. Even component can be further broken into parts to identify the failure modes. Okay, I think it makes some sense? So, let us go to preliminary hazard list. So, first what I will do, I will give you the steps what way you will do, and then with example I will show you that how I will demonstrate the steps, and then finally what is that you have to develop your own case. Okay. I do not know your background, because from which discipline you are coming from, but please remember the domain knowledge is very important. So, the techniques and the examples I am giving to you, where technique is domain independent, but the examples are domain dependent. It is not that I am taking examples from all pervasive sectors, all industries. It is basically a particular some industry problem we will be discussing. But if you are, suppose you are from a civil engineering department, civil engineer, then you have to find out a civil engineer domain where you are going to use this technique, and accordingly you have to translate, you have to use this domain independent technique into your domain based on the examples as a guidelines. Okay. Thank you. Let us see that what you require to know for doing PHL. Please understand design knowledge. By design knowledge, what I mean to say, you must know your process or the system. Better word, we will be using the word system, because it encapsulates everything. The system breakdown up to component level, parts level, the function that each of the components will perform, the interdependency between the components, then subsystem versus subsystem, system versus subsystem, the cross functional dependencies, all those things. Then what are the parameters that are applicable, what are their design intent, are you can you just represent it schematically, when operation starts, how it starts, what are the operational sequence. So, what are the all those things, operation maintenance, all those actually things, how it will be performed, those will come under design knowledge. So, design knowledge is very important. If you do not have the system knowledge of system design, then you cannot break it up to component level, and if you do not know the component level functions, the subsystem level function also you will not be able to understand. So, that is design knowledge, and it is a vast thing, but suppose if you are a mining engineer, then I understand that you know the methods of that mine design, maybe it is underground or open cast. If you are a metallurgical engineer and working in a steel plant, I am sure that you know the design of blast furnace. Okay. Suppose if you are a mechanical engineer and handling maybe the overhead cranes in a factory, then I am sure that you have the knowledge of crane. So, that is what I am saying, that the design knowledge is you must have. Apart from design knowledge, the second thing you must have is the hazard knowledge. By hazard knowledge, what is hazard and how hazard is ultimately converted to accident through different initiating mechanisms, all those things we have discussed so far. So, it is now imperative to say that you are in a position to know that what is hazard, and after going through all the techniques, definitely the hazard knowledge will be improved, but at the basic level whatever I have discussed so far, that you must have, and you must be able to understand what are the hazardous sources, that is hazardous elements, and how the hazardous sources will ultimately occur through different initiating mechanisms, and then finally target and threat. So, those concepts you are for the domain where you are working in. So, that is important, hazard knowledge. Another important one is the lessons learned, that the system for which you are interested in designing. Okay. So, there what you will find out, you will find out that a SIM system, similar system, it has been operational for since long, and there have been many incidents or taken place, or many inspections were carried out. So, as a result, a good set of vocabulary is available with you, the data is available with you. Maybe you have already designed similar system, and or some that your company is having this, then what will happen ultimately. So, when you are talking about design knowledge, already you have learned from your previous design. So, that is also lessons learned. So, all those things you must have. Unless you have these inputs, it is very difficult for you to do any kind of hazard identification, and as such safety engineering will be impossible for you. Okay. So, as a result, you all will agree with me that it is not a independent work, it is a teamwork, and the team comprises maybe design people, operation people, maintenance people, safety experts, analysts, so many. Okay. So, what will be the output? Output will be hazards, mishaps means accident, what are the safety critical factors, and causal sources. In other sense, I can say this will give you the safety domain ontology will be where data safety either through these inputs. I am sure that from hazard identification target threat, the domain ontology you will be able to prepare. That is what is my outputs. So, how do you do it? What is the process? Process is your design knowledge will be compared with hazard knowledge and then identify possible hazards. Design knowledge will be compared with the lessons learned, identify possible hazards and document process. So, that means hazard knowledge and design knowledge will be compared, design knowledge and lessons learned will be compared. So, these two will be compared and these two will be compared, and you will be finding out the gaps, and then you will just continue. Okay. So, what is the methodology? Methodology, it is a first is step 1, define the system. So, define, scope, build the system. So, it is basically your knowledge about the system, understand the system, design operational concept, measure system component, I told you already. Then plan for PHL, what is the goal? You define worksheet, schedule, process, identify a system element, function to be analyzed. Once you have define the system, then system specific goals, subsystem specific goals. Okay. You may be interested to know only the high severity accidents, then that will be your PHL goal. You may say no, I do not want to leave anything left. So, detailed goal you discuss. Then select team. If you do not have team, you cannot do it. Dekho, discipline, design, test, manufacturing. So, different discipline people must be there. Then this team will acquire data, acquire all necessary design, operational, process data needed for the analysis, equipment list, functional diagram, operational concepts, hazard checklist you find out, previous lessons whatever learned, all those things you bring, then only it is possible. So, after that what happen? Once you have the knowledge data, conduct PHL. In PHL what you do? Construct list of hardware components, evaluate conceptual system hardware, compare with hazard checklist, operational function compared with hazard checklist, then identify and evaluate system energy sources, compare with energy hazard checklist, evaluate system software function, compare with system hazard checklist, evaluate possible failure states. So, that means as I told you that there will be component, there will be your software. Okay. So, you have to, there will be different hardwares. So, all those there are different functions. So, okay, that specific design knowledge you have hazard checklist, and then compare them and find out this. Then what will happen once you do this, you will have a hazard list. Now, hazard list, then recommend safety guidelines and design safety methods, and then document. Okay. So, this is what is the process. So, methodology, checklist you require checklist, human hazards, different accidents, general hazards, energy sources. Then what is the system list? There will be hardware, there will be different source, function, software, and different kind of hazards. Then you have a documentation table. The table is like this. You see preliminary hazard analysis, system element type, what kind of it is, it's a equipment, it's a process, whatever may be. Then you number them, then what item name, system item name you write what are the hazards, what are the hazard effects and comments. Okay, these things you have to prepare. This is what is hazard list. I will give you one example, and before that I said that you must have the hazard checklist. Here we are basically looking into hazardous energy sources. You see that starting from fuel, propellant to nuclear and cryogenics, there are 22 energy sources. I have taken this from this book, Kumamoto and Hanley Probabilistic Risk Assessment. Similarly, you will find out that there are different hazardous persistence events. It can be acceleration, can be contamination, can be corrosion. So, that means you require to have checklist. The checklist related to everything, and then design knowledge will be compared with hazard knowledge, and design knowledge will be compared with lessons learned, and follow the checklist, find out the gap, document it, and the documentation form I have already given to you. It's a very much your domain knowledge specific. Let us see this. What is this? It is S missile system, weapon control system, and then is missile system. I have taken this from the Ericsson book. So, suppose this is the total system, S missile system. It is two subsystem, weapon control system is this, and this is the weapon missile. Now, again if you further break down the missile, there will be overhead, there will be battery, there will be computer, destruct, fuel, rocket boosters. So, these many components are there, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Okay. So, these similarly if you see this one, this can be further broken down also. Now, what is required if you want to really do you must know not only this, you must know this. What is this? You see intended equipment list. The missile is all components, weapon that control system components, what are the functions, what are the energy sources applicable, and what is the stage, different stage. So, and when you basically talk about missile launching, you see that there are different phases. That is what we are saying, the system knowledge. You take your own system, are you able to break in this manner or not? If not, then you are not fit to do it. Then definitely you see that in the team somebody else is there or not. So, you make the team in such a manner that they will be able to do it. So, missile launches, missile storage in land storage site, missile transportation to ship, missile storage in shipboard magazine, missile installation in launch tube, missile in standby alert, missile launch sequence, missile flight to target. These are the different phases. How the PHL is used, just I am showing you the documentation part. You see system hardware is the system element type. That means you are first going through hardware, then software, humanware, environment. So many things will be there. Na? So hardware, system, missile structure. This is my list 1. What are the hazard? Missile body breaks up, resulting in fuel leakage and ignition source causing fire. Then hazard effect is missile fire. So the missile body breaks up, resulting in fuel leakage and ignition. So that means hazardous element and initiative mechanisms are told here. Missile body, because missile structure, this is the hazardous element. What will happen? It will breaks up, resulting in what? This once this breaks up, fuel leakage, ignition source, then fire will take place. Fire. Who are target? Definitely the people and the property. And common mean in which operation time? In the ground it is happening. Similarly, the same system element missile structure will be having another list. Missile body breaks up, causing missile crash. So causing fire and another is causing crash, missile crash in the during flight. During ground operation this will take place, during crash this will take place. So in this manner you will, once you go for one hardware to another hardware like missile engine, then engine fails to start, incorrect target, unsafe missile state and fuel release. This is the comment. Missile engine fails during flight, resulting in crash, incorrect target. So you have to prepare a list like this. So what will happen once you take all the system element type from hardware to software to humanware. Okay, when you want entire system breakdown structure you make and you find out all the system items. So for every system item you may have one or multiple hazards, and all those things once you list for a system, it may be hundreds of hazards will be there. So that is important, that list we want to find out. So for this system there will be many more hazards, but I have shown only this only 1, 2, 3, 4, but the list is very long. I request all of you to go through this book written by Ericsson, and you will find out very interesting book, and lot of explanations are also given for this. Now I will give you one case what we have done. It is a basically material handling case in a steel melting shop. Other I can see in a steel plant. There is from blast furnace through torpedo, hot metal from blast furnace by torpedo. Hot metal, blast furnace, liquid metal, very hot, more than 1000 degrees centigrade. So that what will happen? Hot metal from blast furnace with torpedo, it will come here, and then there is a transfer ladle, hot metal unloading from torpedo to transfer ladle. Then hot metal transfer by EOT crane will transfer this to desulfurization unit. Desulfurization of hot metal by injection of CaC2 and magnesium Mg, that is happening here. And then what happen after desulfurization? That slag will send for recycling, but the desulfurized hot metal will transfer to by EOT crane to converter, that is steel melting shop. So conversion of desulfurized hot metal to steel to that BOF. Okay. So basic oxygen furnace. So then further. So this is what is the total that hot metal handling in a steel plant. So that other one, that a crane is EOT crane is used. Suppose we want to do the preliminary hazard listing for this, then what you require to do with reference to material handling, you must know what are the components or what are the different system types. First of all, hardware based, if it is mostly of hardware type. So torpedo, ladle, then crane, then definitely desulfurization, then SMS. So all those things, and SMS and desulfurization, there are some processes taking place. There will be obviously when you talk about crane, operator is there. There are software also in between, some program will control. Okay. So for the time being, I will just show you suppose torpedo, what way we can do this. So, see, system item is torpedo, system item is torpedo. Now, hazard, this is additional thing we have added, but from here you can see hazard, that fuel leakage, then what are the hazard effect? Engine fire, possible human deaths. So, in this manner several hazards are identified, that is what is the listing of hazards. So, to make it ease of identifying the energy, different kind of energy are considered like chemical energy, thermal energy, mechanical energy. It all depends on your knowledge, you can do. So, the basic documentation framework what I have given, that is fine, but apart from this also you can augment it. There is no hard and fast rule that will be used, but please keep in mind that hazardous element, initiating mechanisms, target and threats, the entire path that must be completely enumerated for every system item. There will be multiple such hazards. So, here 1, 2, 3, 4 like this, so many hazards we have identified. See, this is torpedo, then ladle and crane, converter, so many things. Okay. So, let me conclude what you have learned here, that we said that there will be different techniques, more than 50 hazard identification techniques are available, hazard identification technique. It is not that all techniques are applicable everywhere. Broadly, there will be process hazard, there will be equipment or machine hazards, there will be human hazards, there will be software hazards. These are broad things, these are important. So, you have to, and another important one is that system knowledge. So, system to subsystem, then subsystem, and finally, maybe all the components. This structure is very important. So, there in the system there will be definitely hardware point of view, then process, equipment, software point of view, software will be there, human will be there. You have to first identify, maybe you do this kind of breakdown and finally at the component level you come. Otherwise, you can do also, suppose you consider the hardware, find out that every hardware item how it fails, what are the hazards available there. So, what are the hazards there, then it is better to have the checklist. So, mostly in large plant with high risk, the energy is very important one. There are energy sources starting from your gravitational energy to high level energy like your explosive, all are available there. So, all hazard, when you take a hazard, a system item and compare with the energy sources, you first see that what kind of energies are sourced there, and then if you have the functional knowledge of that system item, and if you know that how that system item is interlinked with other system items also. So, then what happen, you are in a position to find out the initiating mechanisms. Few initiating mechanisms related to the system item only, but few are dependent on maybe other things, but whatever may be the thing, that system item one identified, then all the hazard, using hazard checklist and hazard energy sources, you will be able to find out identify the hazardous elements, and using the hazardous process and element, the initiating mechanisms can be identified. And obviously, because of the system knowledge and operational knowledge, you will be in a position to know what is the target and threats. So, once you do this, then your hazard list is ready. For example, suppose I take a system Okay, there are suppose 5 hardware item, suppose 2 software, and let it be 1 operator. So, a 5 hardware item, maybe every hardware item there are let be 6 number of hazards. So, that is 30, need not be everything has 16, someone 5, someone 6, like this, the 30. For 2 softwares you may get another 20, for 1 operator you may get another 5. So, maybe 55 hazards you will find out. By hazards, 55 hazards, I am talking about hazard triangle. So, 55 hazard triangle you can develop. Okay. So, this is what is hazard list, and I hope that it makes sense, and because we have shown you 2 cases also, if you are not able to understand, you just repeat the video and go to the case again, pause there and see that what is written, and in this way you will definitely learn the hazard list. Okay. Thank you very much.